Mr. Brewer with the Hawaii Department of Health, broadcasting from Honolulu, Hawaii. Thanks for joining this webinar. We have a really good crowd today. I'd also like to thank my co-author, Manny Nagaya, I believe is in Phoenix, Arizona at the time. Manny and I have been working on these case studies actually for well over a year in coordination with a lot of our colleagues on the mainland. So today is the first part of a two-part webinar on the use of TPH data for the risk-based evaluation of petroleum releases. Today, part one, we're going to just give an overview of TPH risk and how to develop screening levels and such. It's one of my favorite quotes from Confucius. There are three methods to gain knowledge. The first, reflection, is the noblest. That's kind of what we're doing today. The second, excuse me, imitation is the easiest. And the third, experience, is the bitterest. So reflection is where we sit back and talk about what we know, what we've learned, the lessons we've learned and such. Imitation, I like to think of as guidance, where we start to write these things down so we don't have to repeat the same mistakes. We can learn from each other's experience in the past. The third, experience, we're going to talk about that today. So how to avoid some of the problems we've had assessing, remediating, and managing petroleum contaminated sites in the past. So we split the webinar into two parts. Part one, again, is TPH Basics. And I'll mention this in a minute. A lot of this is covered in the ITRC TPH risk document that's in preparation now. So in this segment today, we'll talk about TPH facts and fallacies. We'll discuss potential environmental concerns, really for all contaminants, but especially how they apply to petroleum contamination. We'll give a brief overview of TPH chemistry and toxicity, and how carbon range and TPH screening levels can be developed. We'll discuss some about TPH versus BTEX risk. Now, all these subjects can be really complicated when you start looking at it in detail. We're only going to hit the basics. We give more details in the document that we prepared. In part two, case studies, we review 5 case studies that reflect a lot of our collective experience. First is for a former fuel tank farm. Second is the case study for active gasoline station. Third is the ruptured oil pipeline in the middle of nowhere. Fourth is a diesel tanker that's flipped over in someone's front yard. And the last is for an oil and gas field. Now, these case studies, as presented and included in the document, are all hypothetical, but they're actually based on real-life experience, sometimes a compilation of different sites. And a lot of the data we present in the case studies, most of it is actually real data that we pulled in from different sites we've worked on. So today we're going to go over part one. Also, just in a matter of addressing time, I want to cover the first case study, the former fuel tank farm. Part two on Wednesday, I'll review very quickly some basic ideas we covered today and basic ideas of the tank farm, and then we'll focus on the last 4 case studies. Quick review of some references. This TPH risk case studies document, we titled it The Collection and Use of Total Petroleum Hydrocarbon Data for the Risk-Based Evaluation of Petroleum Releases, Example Case Studies. It's published by our office. Latest update, August 2018. I noticed a typo in the document yesterday. Well, there'll probably be a September 2018 edits update to it. So any ideas that you have or comments, suggestions, please send those to us, to Manny and I. Second, reference risk-based TPH action levels or screening levels published by our office. They're very similar to California's environmental screening levels, which I helped initiate in the late 90s, early 2000s. It's called, our document's called The Evaluation of Environmental Hazards at Sites with Contaminated Soil and Groundwater, last updated fall 2017. This includes about 200 different types of chemicals and compounds, including TPH. Another reference is petroleum vapor intrusion. This was a field study done by myself and several consultants here in Hawaii and on the mainland. Risk-based evaluation of total petroleum hydrocarbons and vapor intrusion studies. In this case, we went out and collected vapor samples at sites with different types of fuel contamination, especially diesel, also some gasoline, and looked at the detailed carbon range chemistry of the vapors and get a better idea of what was driving risk, what's the main chemical concern in the vapors. So all these, you can see the reference for these documents here at the web page where you can download them, access them. We have some recorded webinars on petroleum vapor intrusion posted to our YouTube web page, and you can also download the slides from there. Some related references. So one point I want to make is this is nothing new. In Massachusetts, in a TPH criteria working group, in the early mid-90s, developed guidance on this topic. Massachusetts was the first state to actually develop screening levels for TPH and for carbon ranges and use them in their guidance. So they've been in their guidance for 20 years. Hawaii, California, and a few other states adopted these. These other references you see here all are reviews of toxicity factors proposed for different carbon ranges. We'll look at that in a minute, that collectively make up TPH. So there's been a lot of reviews of toxicity factors and fate and transport parameter values for carbon ranges and such, and for TPH in general over the last 20 years. US EPA reviewed toxicity factors for carbon ranges. 2009 includes those in their regional screen level guidance. We use those in our guidance. We might make some modifications to them based on these other publications. And then most recently, ITRC document, I think it's to be published into this year, early 2018, TPH risk evaluation at petroleum contaminated sites. Here's the ITRC document. Outline in general what's in the document, and Manny and I are both members of this team. It's a background of TPH risk characterization approaches, kind of review of historical approaches. So there are a lot of details on the chemistry of TPH, especially degradation products. That's been one of the more newer advancements we've been able to make, degradation of TPH in groundwater and toxicity of degradation compounds. It's a discussion of conceptual site models, investigation strategies, a review of basic human health risk assessment approaches, some details on ecological risk assessment as they apply to petroleum, some risk models, risk calculators discussion are included in there. And there's a really interesting, useful, I think, discussion of management of petroleum contaminated sites. That's really what a lot of our work comes down to. We're never going to clean up all the petroleum that a lot of these sites work on, so how do we manage it in the long term? And then the last part, there's a summary of the Hawaii DOH case studies. Now, these case studies are actually intended to be an appendix to the main ITRC document, but just due to limitations on the length of the ITRC document, we decided to publish them separately rather than skim them down and lose a lot of the details. So we published them separately through Hawaii DOH, Department of Health, and then they're referenced in the ITRC document. There's a short summary there. And a lot of the case studies we're talking about today, they all were prepared in coordination with ITRC team members. So the TPH Risk Case Study Report organization, here's the main report, is again an overview of risk-based approaches to TPH. Past work has been done and such. Evaluation of section on how to evaluate existing TPH data for sites and include those in a risk-based evaluation of TPH. We also discuss common risk assessment problems associated with addressing petroleum contaminated sites. One of those is focusing too much on direct exposure when you could have some other problems at sites, or only looking at benzene or something and not addressing TPH. Sometimes it's a problem, sometimes not. And then an overview of the case studies. Attachment 1 gives all the case studies and the details for those we'll be discussing in these webinars. Attachment 2 discusses categories of petroleum release sites, more of how we organize the case studies. Attachment 3, potential environmental concerns. Again, a lot of details. What is direct exposure? What is vapor intrusion? What is gross contamination? Attachment 4 gets into a detailed summary of carbon range and TPH screening levels. A lot of these are screening levels published by the Hawaii Department of Health, but it's a compilation of screening levels and approaches in different states on the mainland. And then attachment 5, which I think is one of the more interesting parts, is how to develop screening levels for TPH-related degradation compounds in groundwater, or as we call them, metabolites. Okay, so let's get started here. The first, TPH risk fallacies. A lot of these I mentioned, they're fallacies I had when I first started in this line of work in the 1990s. I'll show you some great pictures from that, so lessons learned. And the first is assessing TPH risk is complicated. And so TPH risk, and it can be quantitatively assessed in the exact same manner as individual chemicals like BTEXN, benzene, toluene, ethylbenzene, xylene, naphthalene, and other pHs. These approaches, again, were developed in the 1990s. The main debates and discussions since then have been on the toxicity of the different carbon range fractions. We'll mention that in a minute. So it's no more complicated than it is for any other individual compounds. The second common fallacy, and again one I had for a long time when I first started, is TPH only needs to be considered if benzene and other individually compounds are not present, or if they are present, they're below their own screening levels. Well, that can be true, but a lot of times it isn't true. The TPH component of petroleum, which we'll talk about quite a bit now, can still pose a risk or some environmental concerns when concentrations of BTEX and naphthalene and other pHs meet screening levels. I think a lot of us who've been working in the field at these sites and have seen the sites realize this, and we always realize something's wrong. My benzene is meeting my screening levels, but this site still reeks of gasoline contamination, so we're missing something. Again, that's not always the case. One thing we learned from our vapor study, where we went out and did a lot of testing of vapors, especially over diesel sites, is that TPH always drives vapor intrusion risk over benzene, naphthalene, and other individual compounds for all diesel release sites and jet fuel sites, and also for a lot of gasoline releases. We're guessing around 30% of gasoline release sites. So what does this mean? It means that if you reduce the concentration, say, of benzene and soil vapor down to some screening level vapor intrusion, your TPH levels can still be very high and still pose a problem at a site. And this is all published in a paper we published in 2013. So we have a good handle on this, I think, for vapor intrusion. One issue is published studies relationship between TPH risk and BTEX, naphthalene, and pH risk for soil and water, especially for soil, are not available. No one's ever looked at that and looked at the data and said, if we reduce benzene to target screening levels, cleanup levels, are we also taking care of the TPH at a site? So this is one of the motivations for preparation of the ITRC document, is to review all the different approaches for developing screening levels and cleanup levels for TPH risk. And then compare that, go back and look at some of the gasoline sites, especially we've been working on in diesel sites, and see if we are catching all the contamination when we only cleanup is only based on BTEX and not on TPH itself. This can create a lot of angst, I think, for people, including myself in the past, who are only using BTEX and individual compounds to clean up sites, petroleum contaminated sites. One thing we've seen, though, is that for UST sites, especially older ones, when we had high benzene gasoline releases, you can actually do a pretty good job cleaning up a site if you're only looking at the benzene. And that's because benzene was already at a high concentration in the soil. As long as you use like a target 10 to the minus 6, 1 in a million excess cancer risk, you're going to catch most of the contamination. And also at a lot of these old UST sites, in the field, we were pretty much digging out what stunk. You dig out all the stinky dirt, maybe you have to leave a small amount in place, even if the concentrations are kind of high for benzene or TPH or whatever. There's really not enough mass left to pose a long-term risk. So that's, I think, even though we were missing some things, potentially while only looking at benzene and BTEX, we still did a pretty good job of cleaning up most of the UST sites. It's the newer gasoline releases that have very low benzene levels in them that we may be missing something. And for vapor intrusion, you really need to be looking at TPH all the time also. A quick review of potential environmental concerns posed by TPH contaminated soil and groundwater, and really by any type of contaminated soil and groundwater, really depending on the contaminant. So the first thing most people think about for contaminated soil is direct exposure. So you hear a kid playing in some oily, contaminated dirt. So that's an incidental ingestion, inhalation of vapors, getting it on dirt on your skin, having it absorbed through your skin. Really, one of the main risks for petroleum is actually inhalation of vapors for gasoline and diesel, more than, say, a kid or an adult even instantly eating some soil. That's for human health risks. Second common concern is ecotoxicity, flora and fauna. A lot of these I've seen people try to develop some screening levels for ecotoxicity for petroleum, but it's really site dependent because flora and fauna are so different in different places. Third common potential environmental concern is vapor intrusion, where you have a building that's under lower pressure inside than outside with gaps in the floor. It can pull vapors up through the floor of the building, intrude into the building, and impact indoor air. Now, what we've seen in studies, and there's a lot published on this, is that this is especially a concern when you have LNAP or free product in soil or in groundwater within 15 or even maybe 30 feet of the base of a building. Fourth concern is leaching of petroleum contaminated fuels, again, especially gasoline and diesel, and then contamination of underlying groundwater. One point we try to make in the ITRC document, hopefully it'll get put in there, is the leaching models really aren't that accurate for petroleum, or really for any chemical. We're trying to come up with some better lab-based approaches for looking at leaching, but you can develop screening levels for leaching. The fifth common concern switching to groundwater is the impact of especially dissolved phase plumes to drinking water wells. Again, for petroleum, most of the dissolved phase contamination of petroleum, by the time it gets to a drinking water well, is probably going to be TPH-related degradation products. So it's not, strictly speaking, hydrocarbons, but they're breakdown products of hydrocarbons. And as a default, we assume that these breakdown products have a similar toxicity as the parent compounds. So a lot of research now going on about that. Another potential environmental concern, especially we see here in Hawaii and San Francisco Bay Area when I was there, anywhere near shorelines, is discharge of petroleum-contaminated groundwater into streams and along shorelines. And I remember some sites when I was working in San Francisco, where if you went out at low tide and walked along the shoreline, look back at your footprints, you'd actually see a sheen in where your footprints are. And these especially cause impacts to benthic habitats. And you wipe out the benthic community, and you're damaging the overall aquatic habitat. And then the seventh, one of my favorite subjects, I guess, is gross contamination, where you have free product on groundwater or free product heavy contamination in soil. And this could cause a lot of problems, not necessarily related to long-term risk, but short-term risk. So let's look at that one a little bit closer. A lot of you who've seen our webinars in the past have seen this slide. This is one of my last jobs as a consultant. I won't say exactly where it is, but this site had passed a risk assessment. It was a former gas station. It had been closed by the state, and they were digging to put in an underground parking garage. And I was actually reviewing the risk assessment for the site when one of our project managers was out on the site, was a consultant helping with just to make sure nothing happened. He called up and said the site's on fire. So I was looking at the risk assessment. How can the site be on fire? It passed a risk assessment. But when you look at it in detail, the risk assessment only looked at benzene. If we had known, this is back in the 90s, to check for TPH in vapors, we would have realized we had flammable gasoline vapors in the soil, even though benzene vapors are fairly low. One thing I always want to point out, the local regulator for this site was insisting that additional cleanup needed to be made, but the state cleanup fund wouldn't cover it. So that's what gross contamination is. It's especially biggest problem we have digging into these old sites redevelopment is short-term vapor emissions here. You start to have a problem with workers, transitory effects, health effects, nausea and such when high vapor is coming out and they waft over to adjacent properties and cause problems. One site I worked on for a diesel tank, and yes, diesel is volatile, excavating diesel contaminated soil. The vapors went across the street and got sucked into the HVAC system of an adjacent building, and they had to evacuate the entire building. So it's these kind of surprises we don't want. And that's where gross contamination screening levels really come in handy. It's just general odors and nuisance problems, explosive vapors, a big issue. If you're not aware of this ahead of time and you're developing the site, runoff of sheens from stockpiled soil and having to stockpile and manage all of this soil, interference with construction. No developer wants oily equipment to shut down construction projects, interference with subsurface utilities and such. So gross contamination is it's something you know when you see it. It's a big issue for petroleum contaminated sites. So that's a general overview of risk-based screening levels. Next, let's look at potential environmental concerns. So quick notes on risk-based screening levels. And strictly speaking, for risk-based, like for direct exposure, risk is equal to toxicity times the dose. So risk isn't just associated with toxicity. Something can be more toxic than another chemical, but doesn't necessarily pose a higher risk. Dose is equal to the concentration in the media, it may be air or groundwater, soil, times exposure. If you rearrange these equations, you can calculate a risk-based screening level as the target risk, like 1 in a million cancer risk or non-cancer hazard quotients of 1 or something, divided by toxicity times exposure. And equations look a lot more complicated than this, but this is essentially what they boil down to. So we can take this general approach and then with different types of models and approaches, we can develop risk-based screening levels for direct exposure to contaminants in soil, water, or air, for vapor intrusion, for leaching, for gross contamination, and maybe for ecotoxicity. So for any type of contaminant, we can develop screening levels. So here's an example of risk-based screening levels for benzene under a residential setting. So you see all the screening levels in pink are associated with direct exposure to human health. I'm not going to go over all these numbers, but you can see direct exposure, vapor intrusion, leaching, groundwater, gross contamination. And then we can do the same thing for groundwater, develop screening levels for each one of these potential environmental concerns using these different approaches. This starts to get really complicated, all these numbers. If you just want one number, say for benzene in soil, we would look at all the screening levels for benzene in soil, and then take the lowest screening level, which in this case might be, let's say it's for leaching 0.3 milligrams per kilogram, and that's what we would call our tier 1 screening level. If you clean up a site to 0.3 milligrams per kilogram benzene, you're going to take care of all these other risks because that's the most conservative screening level for soil. Same thing for groundwater. The lowest screening level for benzene in groundwater is associated with drinking water toxicity, 5 micrograms per liter. If you clean up groundwater to 5 micrograms per liter or never had more than that, you're not going to have vapor intrusion problems or aquatic habitats. You won't be able to taste benzene in groundwater. Gross contamination, the taste and odor threshold is about 170 micrograms per liter. So these are tier 1 screening levels. So how do we do this for TPH? We can do it for benzene and other contaminants. We've been doing that for decades. So the first step for TPH, and this is discussed in the ITRC's document and in our guidance in more detail, is we look at the different fuel types, and then we break them up into individual carbon ranges. And what a carbon range is, it's just a group of compounds, petroleum-related compounds with similar carbon numbers. So in this case, we break petroleum fuels up into 6 different carbon ranges, 2 for aromatic compounds, or they have benzene rings, C9 to C10 compounds, and then heavier compounds, C11 to C22. We can break the aliphatic compounds, or long chains and branches, into 4 different sets of carbon ranges, C5 to C8, they're light-in aliphatic compounds, C9 to C12, C13 to C18, and C19 to C36. So now we're breaking up petroleum hydrocarbons, the TPH component, into individual components. And there are different ways to break this up. This is the way Massachusetts did it to simplify it, and especially they're based on toxicity assigned to each one. So once we have these different carbon ranges, the next step we can do is assign toxicity factors to each one of the carbon ranges, and we can assign weighted physiochemical constants, solubility, volatility, absorption coefficients, and such to each one of these individual carbon ranges. In the same way we assign the toxicity factors and physiochemical constants to individual chemicals. When we do that, then we can develop screening levels for each one of these carbon ranges in the same way that we do for benzene and such. So I'm not going to go over these, but here's a summary of carbon range physiochemical constants. These are especially published by Massachusetts in 2002, and several other agencies that published them. But for each one of the 6 carbon ranges we use to define TPH, we assign a molecular weight, a vapor pressure, a solubility, a Henry's constant, which talks about volatility, a KOC value, absorption coefficient, diffusion coefficients. These all are used to model how the petroleum migrates through the soil. We do the same thing with toxicity factors. So each one of the 6 carbon ranges, we can assign an oral toxicity factor or a reference dose, and also an inhalation toxicity factor, referred to as a reference concentration. And this just describes a safe level of exposure for each one of these different carbon ranges. So if, like for C5 to C8 aliphatics, exposure of 0.04 milligrams per kilogram body weight per day is considered safe, not to pose a risk. Inhalation, 600 micrograms per cubic meter of air inhaled, is considered a safe concentration. The values, first value I show is from US EPA 2009, some modifications from our office. The value in parentheses is from Massachusetts 2002. So you can see they don't necessarily agree, but they're generally in the right ballpark. Massachusetts tends to be more conservative on some of these carbon ranges, like the C5, C8 aliphatics, and less conservative on the others compared to US EPA, like the longer chain aliphatics. This can make a big difference in the screening levels for direct exposure. But we won't get into details on those. That's something that we present in the ITRC document. It really needs to be worked out maybe at a state agency level. Here's some example carbon range screening levels. These are straight from Massachusetts in 2014. Maybe there's some, I added a few things to it. These aren't used in the case studies. They're included in attachment 4 in the document, but we don't really focus on carbon range screening levels for soil and groundwater. But you can see the screening levels here for soil for direct exposure with Massachusetts C5, C8 aliphatic compounds. They have a direct exposure screening level of 120 milligrams per kilogram. Leaching-based screening level, 210 milligrams per kilogram. Gross contamination, and when can you start to smell, especially vapors and such, and gasoline contaminant or C5, C8 out contaminated soil, about 100 ppm. And you can see as you go from the light-in aliphatic compounds to the heavier aliphatic compounds, according to Massachusetts toxicity factors and such, they get less and less toxic. It's actually can be the opposite with EPA screening levels, at least for the C5, C8, C9, C18 compounds. You can do the same thing for groundwater. You can develop toxicity-based screening levels for each one of these carbon range compounds for drinking water. Toxicity, we have screening levels for aquatic toxicity, or Massachusetts does, for each one of the carbon ranges, and for drinking water taste and odor. These are some that we actually more developed recently. For each one of the compounds, all these petroleum compounds, around 500 ppb, you can start to taste it and maybe smell it in the drinking water. So there's a carbon range screening levels. They can get pretty complicated, as you can see. Same thing for indoor air, and you can calculate based on the inhalation reference concentration, the indoor air screening level for the volatile carbon range compounds. There's two aliphatic ranges, C5, C8, C9, C18, aromatic C9, C10. We have a toxicity factor inhalation. We can calculate a indoor air screening level based on that. And then using the subslab attenuation factors we published in a 2014 document, we can calculate concentrations, say, of C5, C8 aliphatics beneath the floor of a building that would pose a potential vapor intrusion risk. So you see here for C5, C8 aliphatics, 197,000 micrograms per cubic meter. Now I won't get into detail on this, but for subslab vapor screening levels for vapor intrusion, they differ with respect to carbon ranges. This is from the paper we published in 2009. So vapor intrusion risk is a lot higher in cold areas of the U.S. because the indoor air exchange rate is lower than it is, say, somewhere in Hawaii. Well, I haven't closed my windows to my apartment. I leave them open year-round. Versus if a building is heated, then it tends to underpressurize the building more and you get a higher vapor entry rate. So vapor intrusion risk is higher in cold areas of the U.S. than it is in tropical areas or warm in other areas. This is reflected by differences in the attenuation factors of vapors intruding into a building. So we can assign vapor intrusion screening levels are going to be different for different areas of the country. So that all gets pretty complicated. Lots of carbon ranges, lots of screening levels. We try to simplify that in our guidance, and we develop carbon range weighted TPH screening levels. So what we can do for gasoline, diesel, and we call them residual fuels is look at the carbon range makeup of each one of these different fuel types. Excuse me. So for gasoline, we know they're dominated by C5, C8 aliphatics, light chain hydrocarbons. There's a small amount of the heavier chain aliphatic compounds, and then some kind of moderate range C9, C6 aromatics. So we know this composition of gasoline, then we can actually calculate a weighted toxicity for gasoline based on the toxicity of these individual carbon ranges. We do the same thing for diesel. There's not much. There's some, but there's not much light range C5, C8 aliphatics in diesel. It's mostly dominated by middle chain or middle weight aliphatic compounds with some of the middle weight aromatic compounds. Again, we can calculate weighted toxicity factors, weighted fate and transport factors and such for these. Residual fuels, the heavy oils, we assume are mainly dominated by long chain aliphatics and then with some aromatics. So this is our default carbon range makeup of petroleum fuels. We can do the same thing with vapors. They're going to be different from the fuels. But for gasoline, it's still, now it's even more dominated by C5, C8 aliphatics because they're more volatile, with just a smaller amount of middle range aliphatics and aromatics. Diesel fuel vapors tend to be dominated by C9 to C18 aliphatics, which coincidentally US EPA considers, a lot of agencies consider them more toxic than lighter chain aliphatics. So again, we have these default carbon range makeups of fuels and of vapors. We can calculate a weighted toxicity factor for gasoline and diesel, weighted fate and transport parameters for these, and then we can calculate fuel-specific type screening levels. So I won't go into these in detail, but again, here's for gasoline, middle distance like diesel, residual fuels. Here's the weighted physiochemical constants for each one of these fuel types: molecular weight, vapor pressure, solubility, Henry's constant, absorption coefficient, diffusion coefficients. All these things are what get plugged into these models to develop screening levels for direct exposure and leaching and such. And so we can take these for TPH residual fuels. We kind of treat it separately. We assume it's not volatile, not mobile. We can calculate weighted toxicity factors for gasolines, middle distillates, residual fuels, again based on this carbon range makeup, come up with a weighted reference dose for each one of these fuel types, a weighted inhalation reference concentration for each one of these. And then using this in the same way we do for benzene, we did for carbon range, we can calculate carbon range weighted TPH screening levels. So now you just get one number for TPH gasoline, one for diesel. And these can be really useful in screening sites, initial investigation, or even cleanup. Again, this is nothing new. Massachusetts was doing this in the late 1990s. We were doing it in California in the early 2000s. So you can see for soil direct exposure is kind of your RSL equivalent. For TPH gasoline, we calculate a screening level of 450 milligrams per kilogram. For diesel, because of these middleweight aliphatics that tend to dominate diesel, it's actually slightly more toxic than gasoline, higher risk. Direct exposure screening level 220 milligrams per kilogram. Residual fuel is not that toxic. You're kind of getting into chapstick or motor oil. 9,400 ppm is for direct exposure. Then you can see the leaching-based screening levels for all these compounds. They tend to go up as the fuel type becomes less mobile. Gross contamination, you can start to smell gasoline in soil around 100 ppm, diesel around 500 ppm. Residual fuels, it's hard to say, maybe 500, but it could even be 5,000 before you start to notice any contamination in the soil. We do the same thing for groundwater. Drinking water-based toxicity screening level for groundwater that we calculated based on carbon range weighted screening levels, 300 ppb. For diesel, the toxicity-based screening level for drinking water, we calculated at 400 ppb, 400 micrograms per cubic meter. You might say, well, wait a minute, diesel is more toxic, right, than gasoline, all these middle-range aliphatics. The thing is, by the time you get into diesel range, most of these compounds are going to be degraded in the groundwater before they ever hit a well, and the degraded compounds aren't volatile, so we exclude the inhalation pathway for diesel. That's why the screening level for diesel in drinking water is higher than it is for gasoline. Residual fuels, not that toxic in groundwater. You have to get up near the solubility. You can see some numbers for aquatic toxicity. Also, drinking water taste and odor. When can you start to taste gasoline and diesel in groundwater? Probably around 500 ppb, maybe a little bit higher. A key point with this is you're not going to be exposed to high concentrations of TPH, especially as gasoline and diesel fuel in groundwater, without knowing it. By the time it gets high enough to pose a real risk, you're probably going to be able to taste it and smell it. Again, we assume that the toxicity of TPH-related metabolites is equal to parent hydrocarbons. A lot of research going on with this. So that's the soil and groundwater. Weighted TPH screening levels for gasoline vapors. Again, we calculated a weighted inhalation reference concentration for gasoline based on the assumed carbon range makeup dominated by these C5, C8 aliphatics, 280 micrograms per cubic meter. That's our reference concentration. We can calculate an indoor air screening level for gasoline, 290 micrograms per cubic meter. A lot of people who do field work will say, wait a minute, that's below background. Well, that's true. It probably is, just to auto exhaust and other things. Then we can calculate a TPH soil vapor screening level under a slab, 91 milligrams per cubic meter. Again, that varies based on the climate setting you're in. So the carbon range makeup of gasoline vapors is reasonably consistent, and you can calculate our default makeup of the carbon range is actually based on US EPA's PVI database, and we can calculate screening levels for each one of these. This allows a direct comparison of your TPH soil vapor data or indoor air data to these screening levels for a quick assessment. You can do the same thing for TPH diesel. I just noticed that I've got, for some reason, the colors aren't showing up here in this slide. I'll fix that and repost these slides, but we assume that diesel vapors are composed of 75% C9 to C8 aliphatics, 25% C5 to C8 aliphatics. So that would have been green. The C9 aliphatics would have been red. So this is highly variable. The C9 and higher aliphatics are the more toxic component of petroleum vapor, so it's something to be concerned about. So you see the weighted TPH reference concentration is lower than it was for gasoline. It means it's more toxic. The indoor air screening level is lower. Soil vapor screening level is lower. Again, this allows a quick comparison to field data. We'll talk more about that later. So that's how the screening levels can be developed for TPH carbon ranges and weighted concentrations. I know it seems complicated. It's not that complicated when you look at it in detail. So next thing is TPH risk is TPH versus BTEX and pH's risk drivers. We'll talk more about this in the case studies. A key thing to keep in mind here is that TPH dominates BTEX in fuels. For gasoline, the TPH component makes up about 75% of the compounds in gasoline fuels. Benzene about maybe less than 5%, way less than that these days. The other aromatic compounds may be up to 20%. For diesel, TPH typically makes up about 97% or more of the compounds in diesel fuel, with just a minor amount of individual aromatic compounds. That's the fuels. For vapors, for gasoline, TPH vapors tend to make up 97% or more of the compounds in vapors. And then for our BTEX, only maybe 3% of the compounds in gasoline vapors. So you have they're not as toxic, but they make up the dominant proportion of the vapors and of the fuels. It's something to think about. For diesel, again, the colors are messed up here for some reason, but it's greater than 99% TPH compared to BTEX. So this is where it comes down to risk drivers. TPH versus BTEX is risk driver. And a key thing to remember here is dose makes the poison. And remember, risk is equal to toxicity times dose, not just the toxicity. So you can have some compound that has a high toxicity, let's say it's benzene, and a low dose can pose a long-term chronic risk, to compose a high risk. But you can also have the compounds, say like TPH, that are lower toxicity, but much higher doses, much higher exposure, can pose a similar chronic risk that can pose just as high as the risk as benzene, or even a higher risk than benzene, depending on the concentration in the soil. If it's a low toxicity, say TPH, low exposure, then it's not going to be a significant risk. You tend to get acute risk when you have something that's very high toxicity and a very high dose, which you wouldn't normally see as far as long-term acute risk with TPH compounds themselves, but you could if you had a high enough dose. So that's a big point to think about, that benzene may be more toxic than TPH, but TPH can pose a higher risk than TPH than benzene just because of higher exposure. So that's a quick summary of those points on carbon range, TPH makeup, and screening levels and such. I know it's complicated. If you got all that, give me a call. We'll give you a job. So just in quick summary points, petroleum is dominated by nonspecific aliphatic and aromatic compounds, collectively measured and reported as total petroleum hydrocarbons, or TPH. Second point, TPH can be measured and reported in more detail as specific aliphatic and aromatic carbon ranges. And we can assign carbon range, physiochemical constants and toxicity factors to these carbon ranges. This allows us to develop risk-based screening levels, or even forward calculate risk for soil, water, and air in the same manner as done for individual chemicals. And TPH can still pose potential environmental concerns at some gasoline sites, definitely at diesel sites and other petroleum contaminated sites, even though concentrations of BTEX and pHs are below levels of concern. This is something we've been looking at really for the last 20 years, and how to make up for these shortcomings and only look at indicator compounds. So that was a quick summary overview of TPH basics. The last thing I want to do here is do a quick overview of some of the case studies, just the former case study, the former fuel tank farm. This is actually based on a site here in Honolulu. It was a former fuel tank farm being redeveloped for a Lowe's store. But we modified some of the specifics about the case study just to make the case study more comprehensive. So let's look at it real quick. Quick overview of how the case studies are prepared and presented. First, we give a quick introduction to the site. We discuss the general setting of the site and the nature of the release, and we discuss the initial site characterizations. We're going out collecting soil, groundwater, and maybe soil vapor samples. And we discuss the TPH or carbon range screening levels applied to the site, the data that was collected, use those to identify potential environmental concerns, and then some few notes on the remedial actions taken and the lessons learned. So let's look at case study number one, a former fuel terminal. So this, again, it's hypothetical, but again, based on real-life experiences. It's inactive. It was scheduled for commercial redevelopment. So you see all these tanks right in here. It's scheduled for redevelopment for commercial industrial use. In this case, it was going to be a Lowe's hardware store. Petroleum type released at the site, gasoline and diesel. Gasoline was mainly stored in these large tanks here. There was some diesel, but this area is more contaminated with gasoline. Along the highway here, there were a lot of fuel pipelines that serve this general commercial industrial area in general, and these mainly had jet fuel and diesel associated with them. So you had gasoline contamination in the upper part of the site, diesel contamination, especially along the pipeline on the highway. Some of the highlighted topics we look at was site redevelopment, vapor intrusion, gross contamination, methane generation, long-term management of the site, because they never clean up everything at the site. Since the site setting is 10 acres, former, like we said, gasoline and especially diesel above ground storage tank facility that operated for 50 plus years. You can imagine a lot of contamination. Planned commercial redevelopment. Climate zone. This is important to think about for vapor intrusion. Again, vapor intrusion is a bigger issue in cold areas of the country than it is in tropical warmer areas. In this case, we're assuming it's in a cold area of the country. So higher risk vapor intrusion. Unrelated pipelines, like we mentioned, along the southern edge of the property. Primary contaminants of potential concern, TPH gasoline, TPH diesel, and BTEX plus naphthalene. It's about 10 feet to groundwater. In this scenario, groundwater is unconfined, brackish. It's not a current or potential source of drinking water, but it's nearby a surface water body. In this case, it was a harbor, and there are storm waters going through the site. They're actually getting in contact with groundwater, and they discharge into the harbor. Site characterization, there's significant L-naphthalene and gasoline contamination identified in the vicinity of the ASTs, and significant L-naphthalene and diesel contamination identified in the vicinity of the pipelines along the street. So soil and groundwater data are tested again for TPH gasoline, diesel, and BTEX and naphthalene. And again, for the work we've done, we really focus on carbon range weighted screening levels for soil, especially. And for groundwater, it's a little bit different issue. We only test for TPH. We don't really see the need to test for carbon ranges at most of the sites we look at. For soil vapor samples, though, in this case, we're assuming they're tested for TPH carbon ranges. It's going to be a complicated site, mixed fuels, so we want better data for the vapors. And also the vapors are tested for BTEX and naphthalene to assess vapor intrusion risk using methods TIA 15 and 17. Here's a summary of the screening or the action levels utilized. Again, for soil, we're focusing on just testing for TPH like we generally have always done for contaminated soil, and just using the carbon range weighted screening levels. Groundwater, we're not worried. For all these, for vapor intrusion, we're focusing on soil vapor. We don't really trust groundwater data or soil data for vapor intrusion. For groundwater, again, we're just testing for total petroleum hydrocarbon. We'll discuss this. We look at the TPH as measured with and without silica gel cleanup, so we can look at degradation and such. But we assume there's similar toxicity between degradation compounds and the hydrocarbons. So we look at the data without silica gel cleanup compared to screening levels for aquatic habitats and gross contamination. Then for soil vapor, we get carbon range data. So here's some of the site-specific carbon range data for the gasoline vapors. And this is real data collected, I don't know if it's from this site or from a nearby site for gasoline. In this case, if you remember the default concentration, we were assuming for the least toxic C5 C8-aliphatics was a lot lower for gasoline. As a default, we were assuming some moderate concentration of C9 aliphatics and heavier aromatics. In this case, it was totally dominated by C5 C8-aliphatics. It was worthwhile to actually get carbon range data for this site. The weighted reference concentration calculated for the site much higher than what our default means. It was, half again as toxic as we assume in our default. So our TPH screening level for indoor air for commercial industrial fairly high, 2,400 micrograms per cubic meter. You could definitely smell that, but definitely less stringent than our default. We divide this by our subslab attenuation factor for cold climates, get a subslab screening level for TPH as gasoline, 1,500 milligrams per cubic meter, pretty high. TPH to benzene ratio, this is really important to look at. In this case, it was 300 to 1 TPH to benzene. Once you get to about 300 to 1 TPH to benzene and lower than that, then benzene tends to drive risk for vapor intrusion. So you really could just look at benzene as long as you use the 10 to the minus 6 risk to address vapor intrusion concerns. Once this ratio starts to exceed 300 to 1, then you really have to start looking at TPH, because TPH is probably going to play an important role in vapor intrusion. So that was the gasoline vapors. Here's the diesel vapors for the site. And in this case, again, this is real data actually from across the street from this actual site. So in this case, again, the diesel vapors are dominated by these more toxic C9, C8 aliphatics, not as much as we assumed in the default, but it didn't really make that big of a difference. There's still a lot of C5, C8 aliphatics compounds at the site because they're more volatile. They're coming out of diesel fuel. And this site reeked. I mean, you could smell the diesel vapors, obviously, when they're digging into it. So we get a much lower weighted inhalation reference concentration in comparison to the gasoline vapors, a lower indoor air screening level, even for commercial industrial use, and then lower soil gas screening level for vapor intrusion compared to gasoline for this site. And here the TPH to benzene ratio in the soil vapors, 54,000 to 1. So there's no benzene in the vapors coming off of this diesel fuel. There was hardly any naphthalene in the vapors coming off of the diesel either. It was fairly old releases. So in this case, the diesel vapors are dominated by these C9, the C12 aliphatics, and the TPH clearly drove vapor intrusion risk at the site. If you only looked at BTEX, if you only looked at naphthalene, you would think there wasn't much of a problem based on the soil vapor data. But the TPH posed significant vapor intrusion problems for the site. So it's a clear case where you can't just look at BTEX. Summary of the potential environmental concerns for the site without any development: direct exposure, construction workers, store workers, customers, vapor intrusion into buildings, leaching of diesel and gasoline from soil, contamination of underlying groundwater, discharge of contaminated groundwater, especially through storm sewers, into aquatic habitats, and then 5, gross contamination. It's something the developer needs to be aware of at a site before they go in and start digging into a site. When you dig into this area of the site, you're going to hit grossly contaminated soil, you're going to hit free product. This is going to cause a lot of problems during redevelopment if you don't plan ahead of time, between messing up your equipment, storage of contaminated soil, vapors emanating from the site. So again, it's a big issue. Potential environmental concerns at the site. It's a key thing: comparison of non-silica gel cleanup and silica gel cleanup data for groundwater indicated, not surprisingly, significant degradation of dissolved phase petroleum contaminated compounds in areas with LNAPL. So really, in this case, you just let Mother Nature do its work for this particular site. There's already a lot of degradation going on. Benzene, again, drives vapor intrusion risk for the gasoline impacted site, provided that you use a 10 to the minus 6 target risk for your screening level and cleanup level. So that means that the TPH vapor intrusion screening levels, they won't be exceeded when benzene, soil vapor, and screening levels are met. So you clean up the benzene, you clean up the TPH for the gasoline contaminated area. In this case, for the diesel contaminated area, TPH drives vapor intrusion risk, even if a 10 to the minus 6 risk is applied to benzene and naphthalene. So in this case, your TPH vapor intrusion screening levels still be exceeded, even though BTEX screening levels aren't met. That was really obvious at the site. You could smell the vapors coming out of the diesel contaminated area, and there's no BTEX or naphthalene in the vapors, or very little. So here's what we really need to give the developers as part of the remediation: a summary of the risk assessment. We call these environmental hazard maps. This isn't exactly how this site played out in real life, but it's pretty close. Here's where the former tanks were. In the area of red is where we had grossly contaminated, gasoline contaminated soil and free product on groundwater. So again, a lot of management preparation before you start digging into this area. The yellow denotes the area where we could have significant vapor intrusion problems. Here's gasoline contaminated area. The green is where you could have leaching problems from gasoline in soil. And then the blue is where you have potential direct exposure problems from gasoline and even diesel in soil. This can be used to develop the remediation plan for the site. And then the purple is where the groundwater exceeds aquatic toxicity screening levels. So we have to start thinking about storm sewers going through this purple area. Here's the targeted remediation long-term management. Then in this case, they cleaned up the grossly contaminated soil at the site and groundwater, got rid of most of the free product they could, cleaned up the areas that pose significant vapor intrusion problems. And then for the rest of the site, just managing in place, leaching, aquatic toxicity, and even some direct exposure. This is all down by the capillary fringe. It just wasn't cost effective and really necessary to clean up 100% of contamination at the site. You would just manage this in the future. But summary of the site remediation and development then: initial remedial actions, excavation and ex situ treatment of contaminated soil is actually carried out at this site. Removal of L-naphthalene and groundwater in open trenches to extent possible. Addition of oxygen releasing compounds. Then use of vapor suppression agents, environmentally friendly, to minimize off-site vapor emissions during excavation and treatment from the grossly contaminated areas. The commercial facility construction phase, preparation of detailed plan for management of residual contamination, soil and groundwater ahead of time, so you're ready when you get out and start doing your construction. So you have plans made for storage and reuse or disposal of contaminated soil, re-infiltration of contaminated groundwater on site instead of putting it into storm sewers or something. Clay seals on storm sewer trenches to prevent contaminated groundwater from discharging into nearby surface water bodies. Installation of a passive vapor barrier venting system under the new building slab. Post-construction, you want to make a map of where the contamination was left in place. We call it preparation of a post-construction environmental hazard management plan, EHMP, for long-term management of remaining contamination for any future work to be done at the site. This includes methane monitoring. Some of the lessons. I'm getting a little feedback. Okay. I think we're having a problem with Skype on the last slide. Okay, I've just paused to see if they can fix that. Okay, they fixed that. Hopefully you can still hear me. So some of the lessons learned: so a well thought out CSM considers all aspects of the project, not just direct exposure. Thinking about gross contamination, construction, leaching, vapor intrusion, all aspects of the cleanup, assessment, and redevelopment of the site. Direct comparison of TPH, total TPH data to carbon range weighted risk-based screening levels are for TPH generally adequate in our experience for characterization of contaminated soil. This also ensures that cumulative risk is considered instead of looking at each individual carbon range separately. And site-specific carbon range data are preferable to assess vapor intrusion risk for large, complex sites, as we showed in this case study. TPH vapors can still pose significant vapor intrusion risk at sites under some scenarios, like for diesel in this case, even though BTEX concentrations meet conservative screening levels. So that was the first case study and a quick overview. I know a lot of information to take in. And again, there are more details in the document that we're posting. So part 2 we'll take up on Wednesday. So I'll give a very quick summary of what we went over today for people who didn't come and join in today. And then we'll cover the last 4 case studies. We'll look at active gas stations, which are, number-wise, that's the biggest issues we deal with for petroleum contamination. We'll look at a ruptured oil pipeline in the middle of nowhere that goes into a marsh. We'll look at a diesel tanker that flips over in front of an apartment building in an urban area. And then we'll look at contamination associated with an oil and gas field. So that's it for part 1. So I'd be glad to take any questions, comments, ideas. One thing I'd point out, these case studies, I think them as a living document, or it will be. We'll be adding to it over several years, adding different scenarios and things. If you can think of, we'd love to get your comments for additional information or edits to it. Okay, so Vicki and Iris, if we have any questions, I'd be glad to address them.
Thanks, Roger. If there are folks on the line that don't have a computer and you have a question, please unmute and then later mute your phone. Other than that, I have one question. And I don't know, Roger, how much you can get into detail on this, but the question is, could you address analytical methods for TPH?
That's a great question, and that's something that's being taken up in the ITRC document. So the ITRC document goes into a lot more details on the chemistry of carbon ranges and such, and there's also a section that discusses analytical methods for TPH, especially we need better methods for groundwater. for water in general. We'll talk about that in some of the case studies. But wait for ITRC's webinars. I think they're going to start end of the year, early next year. They'll get into more detail on that. We'll add some detail in our guidance also.
Okay, second question is, you had mentioned that leaching models are not terribly accurate. How do you define accuracy? What are the new models considering?
Well, the old models, there's two main models that are used. One is a really simplistic model that it's actually included in the US EPA screening level guidance. And that one, it's way too simplistic for any type of contaminant. We don't use it. It doesn't take into account fate and transport. And we know from experience at sites that based on concentrations in soil and where we can look at the groundwater underneath, that these models way over predict impacts, ability of these contaminants to leach out of soil and impact groundwater. And the problem is that the models, they address the absorption coefficient for contaminants. So how easy is it for a contaminant to absorb to soil particles, organic carbon? The problem is, this one person explained to me, it's like Velcro. It's a lot easier to absorb a contaminant, say a ping pong ball covered in Velcro, to something than it is to pull off. So the absorption coefficients used in leaching models way over predict how easy contaminants can be desorbed from soil. That's why they over predict impacts to groundwater. So there's people working on better models and such. I think that the screening levels we use, we try not to be excessively conservative in the models. And I think they're getting close to useful, but for big sites where it's going to be a lot of money, you really need to come up with some better laboratory leaching tests, which in the end are probably going to involve column leaching tests, which tend to be expensive and such for petroleum. It's another topic that we need to do further work on.
Okay. Next question is in regards of measuring soil vapor and indoor air. What TPH carbon ranges for gasoline and diesel do you prefer reported for soil vapor and indoor air?
Well, if you look back at one of the slides, then we note the carbon ranges for volatile petroleum compounds. So if you just look at the carbon ranges, it would be C5 to C8 aliphatics, and then C9 to C12 aliphatics, and also C9 to C10, maybe C12 aromatic compounds. But in the past, even in our guidance, we were looking at higher range aliphatics, say above C12, and to get those you need a sorbent tube. But we really, in all the studies we've done, we just haven't seen any longer chain hydrocarbons above C12 of any significant concentration in soil vapors. So these days we tend to focus on C9, C12.
Okay, that's all I have here right now. Are there any other questions for people on the phone?
Okay, well, if not, then you can rejoin us on Wednesday. Again, I know that was a lot of information. It's complicated to put everything together, but it's like a car. Once you get it together and learn how to drive it, it's actually pretty useful. You don't have to know all the individual components. So thanks for joining us today, and we'll see you again on Wednesday. And I'll be posting updates to the slides as we find correct typos and such after the webinars are over. We're also going to record these webinars and post them to our YouTube webpage. I'll send out an email to everyone once these webinars are posted. So thanks a lot. Aloha, and see you Wednesday.